Hi, this is Dr. Pat, and we're looking at the connections between graphs and formulas. So, when looking at graphs, what do we know about the formulas, the first derivative, the second derivative, that kind of information? And if we've got the formulas, we can do the derivatives, we can do the second derivative. What information do we get out of the formulas to make our graphs or related to the graphs? Okay, so before I begin this, I just kind of want to look at some of the relationships that we have, looking at the relationships between the original function, the derivative, and the second derivative. Okay, so when we have the original formula, like f of x equals 3x squared minus 7, whatever formula you've got, the information we get out of the original formula, we can get the x and y intercepts. To get the x-intercept, you just plug in 0 for y and then solve for x. To get the y-intercept, it's really easy. You just plug in 0 for x and you just calculate. And so those are two really quick, easy points that we can find on the graph. Another thing that we get out of the original function are the y values. So for graphing, we could always just plug in a bunch of x's and then plot the points that we get with the results that we get from the original function. The other thing we get from the original function are the vertical asymptotes, also the horizontal asymptotes. Well, remember the vertical asymptotes, so those are the ones where we get undefined. We get the cases where we have 0 in the denominator, or also we get domain restrictions such as the natural log. It can't be negative, it can't be 0. So we get vertical asymptotes from when things blow up in the original function. And the other thing we get are the limits, the end behavior. What happens on the left side of the graph when we start plugging in large values? Does the graph go off to infinity, or does it level off to a particular y value? Same thing on the right side of the graph. Does it zoom off to infinity, negative infinity, positive infinity, or does it level off to 0 or another number? Then the second thing that we've got to play with are the derivatives. The first derivative, the information that we get out of that is the slope. The first derivative, the values we get out of the first derivative tell us information about the original one, about the slope, those rates of change. The other thing we use for our first derivative is finding those extrema, the critical values. That's when our first derivative is equal to 0, or when the first derivative is undefined, when we have those really sharp corners. Our second derivative, that's going to give us some information about the original function. It's going to tell us how the original function curves. Okay, so we don't have straight lines all the time. There's bends to our graphs. In the math world, we call that our concavity, whether something concaves up or concaves down, curves up or curves down. The other piece of information we get out of our second derivative, when we set it equal to 0 and solve for x, we get our inflection points. These are the values where the points where the curvature changes from curving up to curving down and vice versa. Also, we get saddle points and that kind of information. The combination between the two. Remember that the second derivative is also the derivative of the derivative. And that's why it's second. And so where the first derivative is at its highest point, we get the second derivative. That's when it's equal to 0. So the second derivative, when it's equal to 0, gives us information about the inflection points on the original when the curvature changes. But when we're looking at the derivative, it also tells us when we're at the steepest, the highest rates of change, or the lowest rates of change. And that means back on the original graph, it's where the graph is steepest. So basically the second derivative is telling us how things curve, but also with combination of the first derivative tells us the steepest part of the graph. And so those are some of our relationships. Some other parts of our relationships that you've seen pieces of graphs. If you have a maximum, you have your first derivative equal to 0, and our second derivative is negative, because we need that curve down in order to have a maximum. And then the opposite way, for a minimum to occur, our first derivative is equal to 0 because we're getting that nice horizontal tangent line. But in order to be a minimum, we got to be curving up, which means our second derivative value must be positive. Now in our inflection points, when we see this curvature change here, we have a curving down situation and then it changes to a curving up. Well, when that happens when the second derivative is equal to 0, and we call those inflection points. Now, in this particular case, this one you may appear to be leveling off, or it doesn't, may have a little bit of a slope that's not equal to 0. So when you have an inflection point, that doesn't tell me anything about the slope. You could have an inflection points that are very, very steep, or they basically have a horizontal tangent line. So kind of be careful about that. Inflection points doesn't mean your first derivative is equal to 0. It just means your second derivative is equal to 0. And then also when we have these weird corners here on the bottom left, basically when that happens, our first derivative is undefined. So when things blow up in terms of slope, steepness, or these jagged edges, corners, your first derivative is undefined. And then in discontinuity points in the bottom right, basically everything's blowing up. You got your first derivative and your second derivative. We're not getting answers for. Okay, so that's the beginning of this. This is just kind of setting the stage, looking at some of the relationships. And in the next two parts, we'll be looking at the relationship going back between functions, the formulas, and the graphs. And so we'll be bouncing between those two to really see those relationships. Thanks, and hope this helped. Bye-bye.